In my research, I looked into what a Fourier series is, conditions for functions which can be represented by a Fourier series, why Fourier series are beneficial over other representations, what the Fourier series equation is and how to find each of the components, associated theorems to Fourier series and why they're helpful, and examples and applications of Fourier series. A Fourier series is an infinite series valid globally for all values of x. The series uses a combination of sinusoidal functions, sine and cosine, each with parent functions of period 2 pi, to approximate other periodic functions. Here you can see the graph of a periodic function in green, and a set of partial sums designating the Fourier series in black. As the animation plays, the number of partial sums increase, providing an increasingly better approximation. When the number of partial sums becomes infinity, the Fourier series approximates the corresponding function exactly. The only exception to this is at discontinuity points. The behavior at discontinuity points in the original function will be discussed further. In many cases, Fourier series are ideal over other approximation methods. One of the main reasons that Fourier series is superior is the fact that the accuracy of approximation moving away from the point which was expanded from stays fairly uniform. Another benefit is that the Fourier series are written entirely in terms of sine and cosine terms, which are used commonly and are very easy to take derivatives and integrals of. Lastly, Fourier series may represent functions which have jump discontinuities, whereas many other series approximations require the function to be continuous on its entire domain. So you're probably wondering why we would ever use any other method to approximate a series. There are a few conditions the function being approximated must follow. The function must be periodic, therefore f of x plus t must be equal to f of x for all x in the domain, and the function may only contain jump discontinuities in which there is a finite number of them. This Fourier series equation can be used for all periodic functions of period 2 pi. As k increases, the approximation becomes more accurate to the original function. The Fourier series equation contains Euler-Fourier formulas for a0, ak, and bk. As you can see, the equation for a sub k is equal to a0 when k is equal to 0. The Fourier series equation was set up with the constant term as a0 over 2 to allow the need for only one equation for both terms. Later, we'll discuss what to do in the case that the values for a sub k and b sub k are different for even and odd integers of k. Now we're going to work through an example. In this case, we'll need to find a Fourier series expansion for the given function. In this case, we're looking at the square wave function, which is equal to 0 for x values between negative pi and 0, and equal to 1 for x values between 0 and pi. We are to assume that this function is periodic, so it repeats itself outside the interval from negative pi to pi. In order to find the Fourier series expansion for the square wave function, we must find values for the Euler-Fourier coefficients a0, a sub k, and b sub k. Despite a0 satisfying the same formula as ak, a0 must be computed separately from the rest of the ak's. From equation 2, we have a0 is equal to 1 over pi times the integral from negative pi to pi of the function f of x. Since the functions being approximated isn't constant on the interval being integrated over, we must split the integrand in two, from negative pi to 0 and from 0 to pi. The values of f of x can then be subbed into the series approximation formula. The value is 0 from negative pi to 0 and 1 from 0 to pi. Solving the integrals leaves a0 equal to pi over pi, or equal to 1. Similarly, we must solve for a sub k. From equation 3, we have ak is equal to 1 over pi times the integral from negative pi to positive pi of f of x cos kx. Once again, we split the integrand in two, from negative pi to 0 and from 0 to pi. The values of f of x can then be substituted into the series approximation formula, equal to 0 from negative pi to 0 and 1 from 0 to pi. Solving the integrals leaves a sub k equal to 0. Now we must solve for b sub k. From equation 4, we have b sub k is equal to 1 over pi times the integral from negative pi to pi of f of x sine kx. Once again, we split the integrand in two, from negative pi to 0 and from 0 to pi. The values of f of x can then be substituted into the series approximation formula. It's equal to 0 from negative pi to 0 and 1 from 0 to pi. Solving the integrals leaves 0 if k is even and 2 over pi times k if k is odd. We're now going to take a moment to discuss even and odd index coefficients. In our example, b sub k is equal to 0 if k is even and 2 over pi k if k is odd. In order to deal with this discrepancy, we write even and odd index coefficients separately. b sub 2k is equal to 0 and b sub 2k minus 1 is equal to 2 over 2k minus 1 times pi. Plugging in values solved for the Euler-Fourier formulas, you get 1 over 2 plus a summation from 1 to infinity of b sub 2k minus 1 times sine 2k minus 1 x. None of our existing convergence tests apply. Instead, we must graph the partial sums of 1 over 2 plus the summation from k equals 1 to n of 2 over 2k minus 1 times pi times sine 2k minus 1 x. As the number of partial sums increase, the Fourier series approximation becomes closer and closer to f of x. Recall, when the number of partial sums becomes infinity, the Fourier series approximates the corresponding function exactly, except for at discontinuity points. The previous Fourier series formula was valid for all periodic functions of period 2 pi. This significantly limits the functions which can be represented by a Fourier series. However, in order to represent functions of period t other than 2 pi, we let L equals the size of the period, or t, divided by 2. This gives us the following equation. A naught over 2 plus the summation from k to infinity of ak times cos k times pi x over L plus b sub k times sine k times pi x over L. As you can see, if we plug 2 pi in for t in this new equation, we're left with the original equation. Since we made modifications to the Fourier series formula, we must also have revised Euler-Fourier formulas for a sub k and b sub k. Recall that when solving for a naught, we can use the same formula for a sub k. Once again, if we plug in 2 pi for t, we get L is equal to pi, leaving us with the original coefficients we used for the original Fourier series equation. Two variations of the Fourier series include the Fourier sine series and the Fourier cosine series. You likely noticed that the sine series only contains the sine term and the cosine series only contains the cosine term. Depending on whether the function is even or odd, one or the other can be used to simplify the process of finding coefficients. Recall that sine is an odd function, and therefore the Fourier sine series is used when f of x is odd, and recall that cosine is an even function, so the Fourier cosine series is used when f of x is even. Recall our original example where we were to find the Fourier series expansion of the square wave function. Notice f of x can be translated to become an odd function, so in this case, we could have just used the Fourier sine series. This is the reason why a sub k, which is a coefficient for the cosine term, was equal to 0. When considering the convergence of the Fourier series, we should be familiar with some key terms. A function which is piecewise continuous on an interval can be partitioned into a finite number of subintervals, such that f is continuous on each open subinterval and approaches a finite limit as x approaches the endpoint of any subinterval. And more specifically, a function is considered piecewise continuous if it is continuous on every finite subinterval except for the finite amount of jump discontinuities. The major theorem associated associated with Fourier series is the Fourier convergence theorem. It states that if f is periodic of period 2L and f and its derivative are continuous on the open interval from negative L to L, aside from a finite number of jump discontinuities, then the Fourier series expansion will converge to f of x at points where f is continuous and will approach the average of the one-sided limits at points of discontinuity. Using this important theorem, a discontinuous function can be redefined at points of discontinuity by the average of the one-sided limits. Therefore, when the Fourier series is redefined at discontinuity points, the Fourier series will converge to f of x for all x. Setting up and working with Fourier series has many applications. These uses span many fields, including engineering and the sciences. The concept of Fourier series was developed to solve problems involving heat exchange through various materials. In general, Fourier series can be used in all applications involving wave phenomena such as sight and sound. Specific commercial and consumer applications include music synthesizers, noise-canceling devices such as headphones, audio compression, signal processing. All these applications involve waveforms or periodic functions which are digitalized by breaking them down into simpler periodic functions. In this presentation, we've discussed what a Fourier series is, conditions for functions which can be represented by a Fourier series, why a Fourier series is beneficial over other representations, what the Fourier series equation is and how to find each of the components, associated theorems to Fourier series, and why they're helpful, and examples and applications of Fourier series.